In the last video, we talked about different ways to think about the different joints of the body. We talked about hinge joints and ball and socket joints and very simple mechanical analogies for the joints we see in the body. Unfortunately, sometimes we encounter scenarios where the joints of the body aren't quite so well behaved as a simple hinge that you might put into a door. So in this video, I want to give you a framework for thinking about more complex joints, both in the most complex cases and how we might be able to simplify the way we think about a complex joint so that we can treat it conveniently. So a very good example is the knee joint. In the previous video, I talked about the knee as if it was this perfect hinge that could just rotate around an axis of rotation like this. But unfortunately, for us at least, the knee is quite sophisticated. It can move, in fact, not just in each of the 3 rotational degrees of freedom, but it actually moves in the 3 different, we call it translational, meaning moving in space, translational degrees of freedom as well. So the knee can flex and extend about the axis here, and that's the major motion of the knee. It also internally and externally rotates a little bit. It can even adduct and abduct, rotating about an axis of rotation like this. And moreover, it even slides forwards and backwards a little bit. It slides side to side a little bit, and it can a tiny bit amount. It can move up and down because of the way the knee rotates on the surface of the femur. So if you're doing, for example, a really complicated investigation into how the different ligaments of the knee restrict those different ranges of motion, you might need to treat the knee as we would say a fully 6 degree of freedom joint. But that can get tricky, so we might be in search of a way to try to simplify this a little bit, but not quite so simple as a 1 degree of freedom hinge. I'm going to introduce a topic that's a little bit advanced, but I find it really useful for simplifying the way we think about complex joints. The idea I'm going to introduce is something called a generalized coordinate. Generalized coordinate. So in the last video, we thought about the knee joint as like a pin joint, right? It's like a little pin, and it has one coordinate. It has 1 degree of freedom. It can just move one way, right? And that's exactly analogous to increasing or decreasing this angle right here. The way to generalize this is to say, okay, what if I prescribe a specific path of motion on which the knee joint can move? And I maybe even only give it 1 degree of freedom, but it prescribes a more complex path in 3-dimensional space. This might sound totally crazy, but let me introduce to you a really simple example. How about a screw going into a surface that has, that's threaded for screws, right? So maybe you have some metal plate and it's got a hole and it's threaded for a screw, right? And you've got a screw up here, and you're going to turn it in with threading, right? So you are going to turn the screw, right? Righty-tighty, and that's like a rotation around this axis of motion, right? But here's the interesting thing. As the screw turns, it is translating like this. So really, this system, even though we could only say you can only move it one way or in 1 degree of freedom, by specifying kind of the direction of the threading of the screw, we can give this an additional degree of freedom. So it's like we can almost get it for, in quotes, free extra motion. So just like using only 1 degree of freedom, meaning how far we've threaded the screw into the hole, has allowed us to collapse a simple system or a complicated system into one number. we can use this idea of a generalized coordinate or a generalized joint angle to describe something more complex like the knee joint. Maybe an even more sophisticated example might be a roller coaster. So say you're at an amusement park and there's like a roller coaster and it goes on some big crazy path and then comes back to the start. If you know how a roller coaster works, it's like bolted onto the track, right? And it can slide along the track, but it can only move in one direction. Hopefully only forwards. I guess in principle it could move backwards. But even though the roller coaster has 6 degrees of freedom, meaning it can move around in space and it can rotate and twist and turn, it only has one. We could represent its position using just one number, and the number would be like, how far down the track are you? Maybe you're like right here. So we could reduce this complexity down to, say, a single degree of freedom. Here's an illustration of how you might be able to do that for the knee joint. So this is a really clever idea. By thinking about the knee angle as one number, 1 degree of freedom, but that sort of prescribes the motion of the femur and the patella and the tibia relative to each other, you can collapse this really complicated joint down into just one number. And even though I've been showing you over here in my simulation software, even though I've been showing you this as if the knee joint is a single hinge that can flex and extend, if I can find it here, and you'll notice, by the way, there's a reason why this is labeled knee angle and not, say, knee flexion. And it's because when you manipulate this joint, notice how the patella is like moving up and sliding as I move this. And if you look really closely, you might even be able to see the tibia rotating relative to the surface of the femur. So notice how it always stays kind of like connected to the surface of the femur, or if I can really maybe even show you, it's sliding in that groove, the trochlear groove of the femur. So even though I only have one number that I can manipulate, even though I can just move this one slider, I'm getting some really nice sophisticated three-dimensional motion here. Another example of that is one of my favorite complicated joints, which is the subtalar joint. So I've alluded to it many times, but the subtalar joint has an axis of rotation that starts kind of like back here at the heel. This illustration shows, by the way, how a clinician might be able to palpate and visualize the subtalar joint moving. So it's like spinning around this thing. But the subtalar joint does something interesting, which is as it spins, meaning as it everts and inverts, it slides forwards and backwards just like a screw, just like I was drawing up earlier. So that's another, if you were interested in maybe a more sophisticated motion of the subtalar joint, you could use this idea of a generalized coordinate to allow yourself more freedom, even though you still only have to summarize that motion with one number. To close this out, I want to bring up one more, even more complicated example, but that I think gives you another good framework of thinking about a really complex joint in a sufficient and compact way. So in the previous video, we talked about all these different kinds of joints, which is all great. Quite often, you'll see people talk about the shoulder as if it's a ball and socket joint, which this part of it kind of is. But the problem with that idea is that the shoulder joint, or the shoulder girdle as a whole, isn't just where the humerus inserts into the socket here. Because as you know, hopefully, the shoulder blade can actually slide around on the surface of the rib cage. So here's a cool idea of how to think about that. Let's give this system 3 degrees of freedom for the shoulder joint, for the shoulder socket, let's say. So we've got, it's like a ball and socket with the socket being like the socket here, and then the humerus coming off like this, right? So we got 3 degrees of freedom. We can rotate how we want in those. Then let's say that ball and socket system sits on top of a surface like this. So maybe I mount my ball and socket on a surface. So like that, a little socket here, humerus going off like this. And maybe you could imagine it's like on a little cart or something, like a little like wheelie thing. And that little cart can slide around in 2 directions on this surface. So let's grant it 2 additional degrees of freedom. These are generalized coordinates again, because this is like moving on a curved path like this. This is a really clever idea and a really clever way to think about and isolate the motion of the shoulder blade from the motion of the humerus in the actual, like the joint right here. Quite often in motions like military press or like a pull-up, one of the things that lifting coaches often look at is what's the position of the shoulder blades? Are they properly pulled together like they should be? Being able to think about that as 2 coordinates of like shoulder blade being up and down, shoulder blade being medial towards the center of the body, lateral away from the center of the body. That's a super useful way of thinking about and isolating the motion of this part of the body from the motion of this part of the body. So to summarize, in this video, we saw that sometimes joints are not so simple. And one way to collapse the complexity of a sophisticated joint like the knee or the shoulder is to apply this idea of generalized coordinates, where we give something a limited number of degrees of freedom, often only 1, but we allow that single degree of freedom to prescribe complicated paths of motion. Now, I'm not going to ask you to actually do this and work out the equations to do it, but I do want you to be familiar with it because I found it to be an incredibly useful way to think about some of the more complex joints of the body that don't fall into those simple categories of hinge joint, ball and socket joint, ellipsoid joint.